Okay. Okay, now everything is turned on. Just go again to the header file. Yeah. If the function is made such that it doesn't alter the our current object, only creates a new object, it's good to make it const, and in which case this needs to be part of the implementation as well. Mm-hmm. We might need to add additional chunks, that is correct. Mm-hmm. 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 Yes. Um, I'm just thinking if we can make it deterministic whether we need the additional chunk or not. Yeah, it's not universally easy to figure out whether we need to carry over or not. I think it's fine to allocate a chunk just in case. If it's slightly too big, then it's fine. Okay. So you really do it bitwise for every single bit. Okay. It's commented out, it will not do anything. You can comment out the whole main function and write a new main function at the top if you want not to scroll around. That will not work because we already have multi-line comments. You can use the preprocessor. Hash if 0 space 0 and then end if at the end of main, and that disables our code block. With hash, of course, hash end if. And then you can create a new main. The ID even nicely shows the code as grayed out, so it's apparent that it's not being compiled. We have print to hex. I get that was also homework. I mean, you can check the functions. Is there a body provided to hex and from hex? The two functions to and hex and from hex. You can check whether they have a body or not. No, they don't. Yeah, we can paste it then in the calculator in programmer mode to give us a normal number. Mm-hmm. There's a cheap way how we can inspect the numbers. We can just view a number that is less than 64-bit. Then we can, in the end, cast the resulting data on a 64-bit integer, which the system can handle, and we can just std out it like any other value. So if we use for our chunk something smaller, then we can reliably test that everything works correctly. Currently we are using short, so that's perfectly fine. May I use the mouse for a second? No, you cannot cast the class itself. So our data are stored inside pdata, and we need to somehow get access to it. We don't have a function that gives us access to them, so let's make the chunk that need to be const the chunk we should be consistent with our naming, and I will not make it const since we might also want to use this method to modify it. So return, we have to check whether we have mptr, so mptr question mark mptr, oops. Data and null ptr if there is no internal object. Now we can raw data, and we will that might be too small. We also need size. The raw size, and we have size in bytes. It's perfect. Okay, and of course here just 0. So we make helper function in 64, or rather unsigned int. Big int to int 64. That thing takes a const big int reference big int. Now make a temporary variable on 64. Initialize it to 0, and then oh yeah, copy. The destination is our value. Reference, the source is our big int. Get was just for data. I didn't make it const. Then I cannot use it there. Let's make it const. Data now. We take what was smaller, min, as to the min from size of value and big int. Let's say so if raw size. So if our integer would be our big integer would be bigger than 64-bit, then we'll just cut off values. So that would not be great, but it in this case, since we're using it only for visualization, we will be just careful not to run into that issue. Normally you would either want to throw an exception or at least print a log line that some data were truncated, and that might be a problem. Okay, not too much. Okay, oh wait, mem copy. Oh, 1c too much. Well, is that correct? So 3 is 3, and 12 hex is 18. That's also correct. Okay, so now first we add 22 and we subtract 15. Yeah, that looks like it's doing what it should. Okay, that's one way of doing things. So let's maybe use we can comment this out. Okay, and then let's erase it. And let's use something considerably bigger. Maybe something like this. This has two chunks. And what constructors do we have at our disposal? Yes, we have the constructor that works with templates, so we can use 64 and 32-bit numbers. And if we add them, that should... oh, that's a good question. Calculator. Hex. So this is this much in binary plus that. Did this give us a additional one or not? The old calculator, the classic style app, was much more convenient. We can count 1, 2, 4. That fits. So we should. I want something that will add an additional chunk. So let's go start with F here. So if F is first, then it will definitely wrap around to the next value. Whether that's correct is a good question. What we can do. Yeah, that's a good point. So let's give the F here and subtract something smaller from it. But what we also can do is we can just copy the numbers to variables 1 and 2, and then we can just use the CPU's internal 64-bit and this would be nice if this would be hexadecimal, and there is a way to print hex in the with stdout. How did that work? I think I need to first that should, if I'm not mistaken, make it print as hex. Okay, so we have this. We can add more text. It's fine. And sum here should be. Oops. I thought I disabled this automatic bracket creation. Should be, that should be a white string. Should be that's subtraction, so it was 1 minus 2, 1 minus 2, and this should be again hex. We can just copy the thing and just change it to a plus, and then we should be able to easily compare whether it's doing what it's supposed to do. Zack. Okay, we are missing spaces. It might be correct. That looks like it works correctly. Nice. So since we know it works, we can now maybe make a small benchmark. So get the count von die ist kleiner 1,000,000 I. Plus we should maybe make those also a bit longer, so let's add that we have 64-bit numbers. Just quickly check if it will still print it. Oops. If it will still print that correctly. There is a min defined in the Windows header, which is conflicting with the std-min. But that still seems to be working. Okay. Right. So we have 1,000,000 operations, and then let's just add and subtract 1,000,000 times, and then we'll print the result. Get the count minus start. And space, or not space, ms to complete end line. Okay, let's see if this is enough. That was far too many operations, because that took... That's not true. Oh, it was in hex. That is probably true, but we don't want... Did this switch that permanently to hex? Doing something? Yeah, that switched it permanently to hex. Then we need to switch it back to decimal. Why can't I switch that back? That should be switchable. I mean, it might not... no, that should definitely not make a difference. Yeah, but that should be correct. How did we manage to break that so badly? Documentation says I have to specify it after the number, but for some reason it still took the previous. Although here, when using hex, it seemed to work fine also for the first occurrence. Ah, no, it did not. The first one is that's explicitly not what the documentation says. That is confusing. But also this means that we can drop the other ones and only need one, because it apparently statically switches the mode, and then it stays in this mode until we switch it again. Okay, yeah, 3 seconds. That feels like 3 seconds. So this code needs 3 seconds for a million operations. Now we'll make an unfair test and compare with how fast the CPU is with just using test 1 ist num1 plus 2 und num1 minus num2 and num1 minus num2. I should have changed the line there. Yeah, it took 0 milliseconds. I mean, we can make it longer. We can make it 10 million. Just until we see something that's not null, it's still null. 100 million. Okay, so at 100 million, we got something. And we had, so it's not just 100 times. I'm too lazy to calculate. I will just divide the... I will just multiply this with 100. Then we know how much slower that is without calculating that in our head. So it's 10,000. No, it's 10,000 times slower. No, it's 100. It's 50,000 times slower. That's not insignificant. That is not insignificant. Now, of course, what would be somewhat nice is to test this if this would be compiled as a release build, but then it would just completely remove those operations since they are not used for anything. So we cannot easily do that. We could try to contrive something together so that we always add the result to the same variable and then return the variable from the main function so that the compiler cannot see that the result is irrelevant. But just as a proof of concept, I think this is good enough. And since the implementation is so extraordinarily slow, I think it would be good if we try to speed it up a bit. So I can show you my implementation for that. So we need those two. Variables. Okay, so, the first one we just do one by one. Okay, so for the addition, my approach is slightly different. So you did this bitwise, which is a perfectly fine way of doing it, but as we have seen, it is a slow way of doing it. It's, I dare to say, painfully slow, even though the other things are reasonably there are things which we could improve. So for example here this these operations, multiplication, division, they are super slow. Okay, so maybe actually before we try the other implementation, we just see if we can speed up those thingies. Although, is that foolproof? No, it's not. Let's leave it as is. So the thing is, when you are multiplying or dividing by something that is a power of 2, then you can just use a bit shift to the left or to the right. But you cannot calculate the right bit shift from size of t chunk. So even though that would be a power of 2 always, you would need basically what you need is you need to know at which bit which one bit is set, and then so that you could know by how many to shift. And with this size of there is no built-in compiler function that would do that for you. So if you would not have a template but something that uses a fixed size, then we could manually enter the right values and make the bit shifts by hand. But here we cannot. Although the other thing to consider is also that if you would build that in a release build, the compiler might be actually smart enough to see that, okay, the results of these operations are in the end always powers of 2, so it could then decide to replace the operations with bit shifts on its own. But since we are building a debug build, it doesn't do all of these optimizations. So let's return to the initial plan to implementing it. So my approach was different. My approach was to use mathematical operations on the chunks directly, and then figure out if we have a carry value or not, and then set that manually. So it's not as straightforward, but if it works, then it should use massively less operations than what the other implementation required. So first we define a help value int carry is equals 0. Then we make a new variable for our result. Let's call it sum. Right. Then we will need to know the size, so how large the new size needs to be. So int we should use size t, small t. It could be called new size, but doesn't matter. We have max, no, std max in this case then, and we take the mptr view size. We should be so consistent. View size and this. Let's see. That looks nicer. And then from the other, the same. mptr view size. Okay, so we have the size. Of which one is bigger? But we might of course run into the situation where we need to increase the size of. So the way my code works is it keeps just the size of the biggest one, and it then drops the carry. So basically it behaves like int64 would behave if you have 2 int64s with the highest order bit set. Then it will just drop the bit, and you will get a value wraparound. So for now I would here keep the behavior, and we can then look into trying to repair that if we deem that necessary. So for int size 10 e, it's like very much in one's nature to use just int e for the loop variable, but if you want to be formally correct, it's recommended for everything that's a size to use size t, and then you of course need to use for your loop variable also size t, so that you are not comparing different types. E++. Okay, so first we will get a copy of the chunk from each of the values. So the chunk this chunk and other chunk, and of course the sizes might be different. So what we do here is we check if e is less than this, so if it's fine, but size is in we need to divide this count. That will be count, not size, because we want this, because here our u size is in bytes, but we have the whole thing in chunks, so we want to divide by of 10 to chunk. Oops. T chunk. Okay, then we have chunk e count. And my own nomenclature is like size is always in bytes, and count or length is in whatever units the thing has. Although that's not how other nomenclatures sometimes work. Sometimes size is really just always the count, and that is then not great, because it gives you the opportunity to make mistakes like you would have run into here if you would not have been careful. And 0. So we copy this and do the same thing just with the other. So the idea is that we will get either the value of the chunk, or if we are now for the variable which has a shorter internal data set, then we just take 0 and pad basically the the other one with zeros. And we don't care here for aborting early. We just will use this trick since it's quite convenient. Okay, so now we create a new chunk. New chunk is equals chunk this plus chunk other, as simple as it gets. And now we need to figure out whether a carry bit would be set. Now, if we would be doing this like the most efficient way, then we would not be writing it in C++, but we would write the function itself in assembler, and there, after the plus operation, we could query a status flag, and then we would know whether in this operation a carry bit was generated or not. But since we are writing in C and it's already a bit more abstracted from the direct hardware access that we would have in assembler, we need to somehow else figure that out. I mean, the other approach would of course be to write just one small helper function in assembler which we call, which will tell us was the flag set or not. So that would be the most elegant solution, but that would also be a bit overcomplicated. So what we can do to figure out whether the carry bit was set is a set of comparisons. So we check if the new chunk is smaller than this chunk, or the new chunk is smaller than the other chunk. Because if a 1 was dropped, then the truncated values, since they wrap around, then they must be smaller than the values we have added together. It's not as efficient as querying just a status register, because it still requires a couple of operations, but given that we can operate at up to 64 bits per chunk, that is a okay trade-off. So if it happen and we set carry to 1, else we set carry to 0. I mean, we could also make it more efficient and just write carries equals this, or use a question mark operator. Maybe we should do that. Is nice. Question mark wind up with 0. Yeah, that's nicer. Okay. Good. Then we will reuse the variable this chunk because we don't need it anymore. We can set it to our new chunk. And for the new chunk we will make another operation. New chunk is equals this chunk plus other chunk. And then we have another check like this. This time it works slightly differently. New chunk this chunk, new chunk other chunk, and if that is the case, then carry plus equals 1. So then we increase it, capital C. One more. Wait, I have a few mistakes. First of all, here we need to fix that. I got distracted, and first we need to handle the carry thingies, and then we do this. Right now it's correct. Other chunk is only used here. So first we handle the carry from the previous loop iteration, if there is any. Then we do actually our addition, and since we have one carry in, then do our addition, which might create its own carry. So the carry as such might be up to 2. Okay, and then once we are done, we can set we have not resized sum, we need to resize sum as well. Log data. Oops. Yeah. That should be large enough. So sum punct mptr data of e is equals new chunk. That should be correct, and then we can return sum. So first let's see whether it actually works. We can just run this code as is. We don't need this, we can comment that out. Oops. Actually we just want to break it here, we just want to see whether the operation works correctly, and the subtraction will not work since it's an empty function. That looks like we did the right thing, so that works fine. So now let's do the subtraction. And here we are doing it in a somewhat similar way. So when we are subtracting, we can also have a carry in the other direction. So again, we can copy some of the code from here up to here actually. And this sub. Return sub. Okay, so we have the thing, we allocate the thing. Then we more or less behave analogous to before. So p chunk new chunk is equals this chunk minus carry. Now carry is equals new chunk. If it's grayed out, this chunk, or oops. Or new chunk is greater than carry. But in this case, only if carry actually from the previous run was set. If carry is 0, then the second case is ignored. And then of course carry is equals 1 or 0. Okay. Then this chunk is equals new chunk. New chunk is equals this chunk minus other chunk. And now we check if new chunk is greater other chunk than plus plus, or rather plus or is equals 1, capital C. And the last thing is to set the thing to what it was before. Okay, let's run it to see. Oops, yeah, the name of the variable changed. Let's run it to see whether it works correctly. No, it does not, damn it. We have a bug here. That is not great. First thing, let's just see how fast this actually is in comparison to the other implementation. Well, it's the other one was 3 seconds. This one only takes half a second, so it's 6 times faster already. But it's not doing its thing correctly. That's annoying. I mean, first thing what we should do is maybe printed in a more debug friendly way. So we'll print one on the top of the other. So we have then should be double punct add, and here the same for this thing, so that the numbers are nicely aligned. Yeah, don't need the spaces. We can make a double point. Okay, that's good. Now we can compare it in a more. Yeah, so the first one looks definitely correct. The second one does not. It will be annoying to debug. Okay, the first thing we can check whether we can drop some of the number just to make it less complicated. Yeah, that is even worsely broken. Subtract from this. Okay, so let's see what's the simplest case where we can generate a failure. This will certainly be fine because it's too short. No, it's wrong. Let's start with 0. Greater. I mean, apparently something's wrong about the carry operation. And we are subtracting from a bigger number a smaller number, which should be correct. That should be a pretty simple bug, actually. Let's see. So we have here our count for count for. So we are already working with a 64-bit number. Why? Yes, because it is defined as a 64-bit number. Okay. So first for testing, let's knock this down to short and see if it then still doesn't behave correctly. Now if it doesn't go past the chunk boundary, it behaves correctly. So with long, it should already fail. Yeah. But this makes things simpler since we only have one transition between the chunk boundaries. So we have our two numbers. Carry is 0. Okay, so new chunk is 25. The old one is also, so this is not true. This should be 0. Should remain 0. This is fine. Oh. I think I know what's wrong. This should be, the comparison here is not correct. Okay, let's run it. Yeah. We found the bug. Let's quickly go here back to the large numbers. Voila, it's working correctly. Nice. So it's what did I say? What did we say? Only 6 times faster. That's I was really hoping for a much more significant difference. Maybe we should test it. Yeah, it's only 6 times faster. That is undeniable. I was thinking it will be at least 1 or 2 orders of magnitude, so that we come at least close to the ballpark of the native operation. Well, one thing that of course takes an infinite amount of time in comparison to everything else is the memory allocation. So this might not necessarily be a fair comparison to the native case. So let's make this a bit more fair. Basically, we just need that for the result. So let's make this a pointer. Add and subtract. Okay, so let's wait, that other thing is now still set to 100 million. Let's set it back to 1 million and see, because that's also of course possible that yeah, so as you see now, even the 100,000 sorry, even the just 1 million operation takes already 230 milliseconds, simply because the malloc and free are so extremely slow operations. But now we see that our code, if we disregard the need for memory allocation, is only only half as slow as doing it natively, and that's actually quite good. And of course, the other operation would still take the same time, so the optimized not bitwise code is still 6 times faster than the doing everything bit by bit. So we have now two options how we can proceed from here. One would be to implement some memory pool, so that we can speed up the allocations a lot. Or since we only have half an hour left, that probably will not be enough to invent and own. Maybe. We could. That would not necessarily be so difficult. If we go for a fixed size, that is, but the fixed size is of course not the goal of our int, so we want it to be flexible. So fixed size would not be a fair approach. And the other thing what we can try is we can try to benchmark it in release mode, but as said, the problem is that you can try it. It depends how it decides to optimize the code, but we can put a breakpoint here, run it, and then see if we go into breakpoint. What? Why is it not showing anything? Now it's showing how much it actually removed from our code. So we have our get the count. Wait, we're here. So yeah, the loop is just looping without doing anything. That is well, it optimized it away, obviously. So we need to somehow fake around that. And the thing is, if we print some text here or something to the console, that will again be the slowest operation. So we could grab some sort of helper variable. Oops. And then we say temp so equals so add loop subtract something something that will make this needed, and then we can here just std out that, so that the compiler thinks that the result of the operation is not irrelevant. Okay, let's rebuild it and see whether we get okay. It's still decided that that is not relevant. Oh no, wait, now it's doing code. Did it it moved the code around. Okay, wait, maybe they didn't remove it in before. It just starts stepping through it. Because the next annoying thing the optimizer sometimes does it is moves the code. Oh no, the code is still dead. It was not removed. Probably because it doesn't really know what free does at the level of the function call. So let's actually try to run this and see how fast that will be. And but for the other one, let's test whether this one also is still actually doing the code. So step seems to actually be doing everything, so it actually does not optimize that many things away. That's nice. Why is it complaining here? It might be a null pointer, yeah, but we don't care for that. That actually did not. It actually had a worse result. That's interesting. Let's run it again. So yeah, there is no helper code anywhere. We just have our faster implementation and then the machine one. 730, and if we now go to the debug build, it's actually faster than the debug build in the first case. That's unexpected. To configure something here already. Optimization favors speed. Yeah, so optimizations are enabled. The other thing that might of course be a bit of a problem is that the way these memory allocations work, if they detect that a debugger is attached, is different than how they work, at least according to the documentation, when they just do what they want to do. So what we could do is we can run our test application not under the debugger, so we keep the window here for reference, open a new window, and then yep, that was for the implementation significantly faster than when running under the debugger. And interestingly, it didn't change for the CPU implementation, even though we are using here malloc and free each time. But that is almost too good of a result to believe in. Huh? Yeah. But it's reproducible. I mean, the spread is quite a lot, so it's not super reliable. We should add a 0. If it's so fast, then we should just make everything 10 million. The other thing is that the resolution of this get count is only 10 milliseconds, more or less, so it will not be... It's insane, that's really good. I mean, it looks really good because we are losing a lot of time on this, and then only counting only timing the operations themselves would not be that easy. Can we somehow speed this up? What we could do is we could make a function which takes which does not return a value, but which takes a pointer to sub which already has pre-allocated memory. That is reasonable. That would be reasonable. Then we can benchmark the mechanisms more precisely. But before we do that, we could again take a look on the 0 case, so the bitwise code, and then see how much this will take in a undebugged release build. needs some time. Yeah, so it is still 10 times 10 times slower. But that's to be expected if you really do bit by bit. In my code you can process 16 bits at once, and that is more or less the 10 times faster, since we are redoing a few operations a few times, so we lose a factor of 2 again, and then we end up at the previous value. But let's do the change here, that we will have another add subtract variant. Void comma reference out. Oh no, with add was sum, and with the other one was sub. No, this will put here. Once we tested this, we could also test the other code to get a better feeling for that. Right, so basically we just take that. Okay, let's copy everything and then just rip it down. Subtract add. Okay, so we don't need this, and we don't need that, and we don't need that. The rest stays same here. Sub goes away, alloc goes away, and return goes away. And here we have then subtract other comma sub and return sub. And here we will have, so wait, subtract, add. For add we will have, so this goes away, this stays here, alter comma add, this goes away, add, what's wrong with add, sum. Okay, and now let's go to main, and right, so we do not want to memory allocate in the machine case either. And in our case we will have we already have add and sub, so we will just use them test point add test2 comma add small a, and test1 subtract what was it, test2 comma sub. Okay, so now both should run without memory allocation. And I hope the compiler will not optimize this away if we are in release, but let's quickly check that. So here, step. Well, we do it, so this is good. Remove the breakpoint, and here, and here now it's I cannot even breakpoint the loop because it has really killed the whole loop. We always the whole loop is gone because it saw that this is a no operation. So we need the temp, which we will then do something with it. Temp. Actually, we could make temp is I mean this is not 100% fair because we add XOR operation in addition to our addition and subtraction, but the XOR is like extremely fast, so let's just say this is acceptable, and we print it so that the compiler thinks that it's needed for something, and print should be, yeah, it's fine being here. It has still optimized it away. Okay, now it did not optimize it away. But it made the whole thing it mathematically optimized away. So it's just to add operations. Yeah, let's say it's fair enough. I mean, we definitely will need to add a few zeros here and here maybe as well. Let's try with 100 million operations in both cases. Okay, so the top case is not as fast. Yeah, it's still excruciatingly slow. I would have thought that that should be faster because, well, let's see, we have max, we have a division. The division is slow, but we at least don't have memory allocations. Well, apparently, as you see, the CPU always wins hands down with regard to speed if we don't handicap it artificially. So it's what is it, 40 versus 10,000, so it's just 200 times faster than than our own implementation. Well, I mean, it is believable because here I mean, since we want to maintain the result, we at least make this add, and this gave us, these are like 4 operations, but it optimized this whole loop into just 2 operations already. And I guess our own code, we can take a look into how this inside it, how it looks in assembler. Okay, oh, it must have optimized something away because the breakpoint is not triggering. Interesting. Oh, that's also nice. It decided to put the whole function, a whole function count into the whole body of add. It put the whole body of add into our loop. Since we only called the function once, it was thinking, yeah, that's an optimization. Why do a function jump if we can just copy the code and put it in place? But you still see that it's let's actually see how many lines. Just copy this, paste it in Notepad, and then count. Does it show the lines? Yeah, it shows you the lines. It's about 50 lines. So it's about 50 instructions, and the other one, and the second one is another 50. So it's about 100 instructions. And the thing was here just 2 instructions, so that should be at least 50 times slower. And as said, the plus minus instructions are very fast, while we have some multiplication somewhere. Unless it optimized it away as well, and the multiplication is quite a slow operation anyway, so yeah. I guess that much to the benchmarking. Of course, what one could do then, what one would do realistically when we would be using this code would be to just increase the chunk size. So we are handicapping ourselves artificially by requiring a chunk to be short. If we would decide that we want to use this in the production, we would just use a 64-bit chunk size. But then we could not really compare against the CPU because the CPU could not handle anything big anyway. So it's a trade-off. And also as mentioned, there would be much more efficient ways to implement the code if that would be really real production code. So we could solve most of the logic, or rather rationalize away most of the logic around the carry bit if you could just query the carry flag. That brings me on an idea. There are some built-in functions which allow you access to the raw CPU states, but it doesn't look like there is one for carry. We only have 14 minutes left, so I don't think I will. This will be enough time to make a demo and write it in assembler, because in assembler it's like probably 5 lines of instructions and that's it. And then we will get the carry flag out. But the annoying thing with 64-bit compilers from Microsoft is that you cannot use inline assembler. So with 32-bit you could write __ ASM curly brackets and then do something. But the problem is that they disabled that ability if you have 64-bit code. Then you really have to always put your assembler code into a separate ASM file. And I think the reason why they did it is because the exception handling for 64-bit is contingent on there being some definitions set in the assembly file. So if you would write assembly directly in your C file and omit those definitions, then the exception handling would break. So that would not be what one wants. Yeah, I think since the other user had to leave anyways already, I think this is a good point to stop for now. We'll see each other for the lecture in 3 hours, and then we will take a look on something Qt or something like that. We will see what's the next thing that will be interesting. And during the next lecture, I guess we will take a look. During the next exercise next week, we will take a look on the multiply and divide implementations, or we try to make an own memory pool. But with the memory pool, I don't think it's something that is easy to break up into tasks. So that would be just me implementing it. So that's rather something for a lecture, not for an exercise. But I think the multiply and divide will also be quite interesting because I think I might have quite an efficient solution as well. Okay, so see you later. Bye bye.